On the left-hand side, this is what you call a posterior probability. It's called a posterior probability because it's after, it's post observing the data. And we can see that we've gone from HR to this complicated formula here, which I introduced before the break. So what we are going to do is to modify our prior probabilities, which are here and here and here. We're going to modify our prior probability and turn it into a posterior. This is what happens when you've got some information. We are updating our beliefs about who's likely to be right in the light of data. This is a complicated, difficult process. Surely one of them's true, but we just don't know which one. I'm not saying that. I'm saying each one's got a certain probability of being true. How do those probabilities alter in the face of data? And we'll see lots of examples of how this process works. Okay. So first of all, we need to work out some of these things here. We need this, probability of the data given HR. And what was the data? The data was 14 and 6. And HR for Robin's hypothesis, which was, the hypothesis was that P equals 0.5. So it's a binomial probability. Yeah? So this equals 20, choose 14 and 6, times 0.5 to the power 14 times 0.5 to the power 6. That's the binomial distribution which we covered last week and the week before. And what about this one? What's the probability of seeing the data given Annabelle was right? Okay, she said 3/4 of people carried an umbrella. Are you happy? That's just a binomial distribution. You're all looking at it as if it's written in some weird font that you've never seen before. It's just a binomial distribution. It's 20 choose 14, 14 successes out of 20, times the probability, times 1 minus probability. You've seen the formula, come on.
I take it that you mean in factorial, you just use that first.
Huh?
Didn't you have 20 factorial over 14 factorial?
20 choose 14 and 6, yeah? Is 20 factorial over 14 factorial times 6 factorial. Yeah?
Yep.
So now we can just go through this whole process and work it out. Probability that I'm right after we've seen data is equal to the well, I'll just write it out. This probability of D given HR, well, it's this one here, isn't it? It's 20 choose 14 and 6 times 0.5 to the power 20, because I've got 20 altogether here, yeah? You happy where this 0.9 comes from? It's the prior probability of me being right before. That's this one here. That's the prior. Over 20 choose 14 and 6. 0.5 to the 20 times 0.9 plus 20 choose 14 6 times 0.75 to the power 14 times 0.25 to the power 6 times 0.1. Where do all these numbers come from? That's her prior probability. That's 1 minus this. Because 90% of chance the adult's right, 10% chance the child's right. This is the binomial probability of seeing the data given that I'm right. That's what it is. It's the probability of seeing the data given my hypothesis is true. And I say 50-50. And 50-50 is here. 50-50 is here. And this one is the probability of seeing the data given that Annabelle was right with a 3/4 chance of carrying the umbrella. So we just plug the numbers into the binomial distribution. Right? Quite a mouthful as it is there, but we'll see that it simplifies. For a start, I'll just leave that up on the board. We can cancel out the combinatorical term. It just cancels out from everywhere. I'll use red to cancel it out. That's make things a lot easier. Nice, isn't it? So what have we got left? We've got 0.5 to the power 20 times 0.9 divided by 0.5 to the power 20 times 0.9 plus 0.75 to the power 14 times 0.25 to the power 6 times her 0.1. Can we simplify that anymore? I don't think we can we? Why don't we just calculate what that is?
What? The bottom one? Not point.
0.25 to the power 6. All those are those numbers there. And I'm just going to plug them in. And I'm going to cancel, before I even start, I'm going to cancel this times 10 to the minus 7 from the top and the bottom. All right? Equals approximately, because I'll lose all the decimal places, 8.58 over 8.58 plus 4.35. Quite a lot going on here. We started with prior probabilities of 0.1 that she was right and 0.9 that I was right because I'm a grown-up. Now we've thrown data at it. We've gone through this process here. What's the probability that I'm right? It's gone from 90% down to 60% because the data is agreeing with her. She said that 3/4 of people carrying umbrellas, and it was 14 out of 20, whereas I said it would only be 10. So the data is supporting her hypothesis and downgrading mine from 90% down to 66%. Okay?
Is there a 90% chance that you're right, improving your hypothesis?
Yes.
Yeah,
So I've gone from 90% down to 60% because the data is supporting me. She's had a 10% chance of being correct, and now she's got a 33% chance of being successful because the data is supporting me. We'll go through some different examples a little bit later. But you can see how we're going through this process here.
How does that second 20, 14, 6 cancel out in the bottom?
Oh, because it's plus here.
Yeah, but how, like you've got 3 of them, right?
Yeah, I'm cancelling out the top with the bottom. I've got this.
Yeah, but how can one of the top ones cancel out 2 of the bottom?
Because it's multiplying it on both sides. I've got xy over xy plus xz, yeah? And I'm just cancelling the x from the top and the bottom. Yeah. Let me write that out more slowly, yeah? If I've got xy over xy plus xz, that's equals x times y over x times y plus z, yeah? I'm just factorising the bottom. So I'm just cancelling it from the top and the bottom, there it is. Yeah? Let me rewrite this equation in a slightly different way. It's the same formula. All I've done is taken that term there and write it there instead. It's still on the top. It's just multiplied. Times a factor from the data, which is this mess here. So the posterior probability is the prior, which is the probability that I was right beforehand, times the data. And the data acted against me, didn't it? The data acts against me because it reduces my probability of being right. Because I made a prediction. I said about 10 people will have an umbrella, and there was more. There was 14. She said there'd be 15 or 16, and there was 14. So the data supports her and refutes
So
me.
if you've reworked that one and had it as her 0.1,
Yeah.
you would increase that for her. Because
Yes,
it's got
it increased from
0.1.
0.1 to 0.33 because it was 2/3 after the event.
Okay.
Okay. Let's do it again with a slightly different data set. Let's just say that we stayed in that cafe and we counted 40 people. We've got new data. D, 40 people, 30 with an umbrella. So just thinking about it, if I was right and half of the people were carrying umbrellas, it's pretty unlikely that we see as many as 30, isn't it? Yeah? We'll just,
If you were right.
if I was right. So we just go through the same process again. Probability that I'm right. Given the new data, equals, well, I'll just write it out, 0.9, because that's the probability that I was right before we looked at the data, because I'm a grown-up, times probability of the data given I'm right, over the other term. Probability that I was right before times the probability of the data given I was right, plus the probability of her being right times the probability of seeing the data given that she was correct. So what we're doing here, Bayes' theorem, is flipping over the data and the hypothesis. These are easy to work out, but boring. That's interesting, but hard to work out. And Bayes' theorem gives you the link by swapping these two guys round. So let's just try it with 40 people, 30 with an umbrella. Let's just try it. Well, it's 0.9 times probability of data given that I was right, which is 40 choose 30 and 10 times a half to the power 40. That's just the binomial probability. Over 0.9 times 40 choose 30 and 10, 1/2 to the power 40, plus 0.9, 40 choose 30 and 10. Do you see what's happening now? I'm just writing out the binomial probabilities. This is hard. You're going to have to take it away and sit down and go through it until you understand it.
Where's the 0.1?
Where's the 0.1?
Oh, I'm sorry, that should be a 0.1. I am sorry. This one and this one add up to 1. Yes, I am sorry. So I can cancel the combinatorical term from the top and the bottom in the same way that I was cancelling the fraction beforehand. Just cancel that. That just disappears from the top and the bottom because it's a sum on the bottom. Because it's xy plus xz, yeah? So what have I got? Altogether, I've got 0.9 times 1/2 to the power 40 over 0.9 times 1/2 to the power 40 plus 0.1 times 0.75 to the power 30 times 0.2 to the power 10. All right, and just work those out. 0.25. Thank you. All right, I'll just work those out. What's the top one? It's that. And you see it's the same on the bottom there. It's a plus of the same. What's the other one? It's 0.1 times 0.75 to the power 30 times 0.25 to the power 10. Which is that. Oh, here we are. Okay, so what I need to work out is that over that plus that. See what I'm doing? What I'm doing is that if I rewrite this as A over A plus B, yeah? Because it's A over A plus B. And I need to work out what these guys are. A becomes that, and B becomes that, and I need A over A plus B. So that's the probability that I was right.
So the more data you have, the lower your probability.
That's right. It's looking more and more like she's right, isn't it? Because she said 3/4, and by goodness, 3/4 of people are carrying an umbrella. And as it goes on and on and on and on, my position of 50-50 is untenable. If it was like 4,000 and 3,000, there's no way that's going to happen. She's right and I'm wrong. And look what's happening here. The only reason I've got as high as this is because I started out as a grown-up with 90%.
So your daughter is wiser than you?
Oh, it always happens. Who here's got daughters? It always happens. Let me just summarise and then I'll stop. We've got priors. We've got the probability that I'm right is 90%, and the probability that she's right is 10%, because she's only a little girl and I'm a grown-up and I'm probably right.
Can I just so the priors, you just chose these numbers because...
Because they seem to be about right.
Okay.
We'll see examples of where this subjective thinking is actually necessary. Then we throw data via Bayes. Yeah? And then we get posteriors, which is the probability that I'm right given some observations. That should be an R. Which was 0.04. And of course, the probability that she was right is the B over A plus B. That Annabelle was right given the data was 0.96. So it's flipped over completely. Before, I was probably right because we didn't have any data. Now we've got some data that supports her and contradicts me, and it's overthrown this probability here. So she was probably right. There's still a ghost of a chance that I was right, 4%, but she's probably right. This is called Bayesian, or the Bayesian analysis, or updating of priors to give posteriors. All right, and I'll stop there for today. We'll do a little bit more on the tutorial next week.